Okay, so here we go. We've got these two equations, and we want to go ahead and model them. So let's just set ourselves up so that we can do this. And here's what I'm thinking is, here's what I want to plot. I want to plot x equals, okay, so let's talk about this for a second. If you come down here, what we did was we eliminated the parameter. This is actually the x versus y formula, and this would actually be easier to plot. However, as we get more advanced and the ballistics get a little bit fuzzier capabilities, they're bouncing around a little bit weirder, we're not going to be able to do this explicitly. It's called a closed form solution. We're not going to be able to get the closed form solution. So what we're going to do is we're going to go ahead and revert back to our original ones, okay? And so that's what we're going to go ahead and model. So we want V naught times time times the cosine of theta, okay? Let's see if it works like this. And then y equals, okay, now I have negative 1/2 times g times t squared. In MATLAB, I don't know if I have to put the dot. I think I do. Dot square. So that's like element by element, and then if I find out I don't need that in MATLAB, we'll fix that. V naught times t times the sine of theta, right, plus y naught. Okay, so let's go ahead and give ourselves a scenario here. So let's say we'll make it really easy. Oh, we don't use that. We use this. A ballistic is fired at 1 meter per second. We'll just put everything at 1, okay? At 45 degrees from 1 meter high. Do we need anything else? At V naught equals 1 meter per second. Okay. Then we can go through and we can really build this thing out. Okay. So let's just go through and do this. Things that would change frequently. Right? Theta. Okay, that equals 45 degrees. Now hold on. We're in MATLAB, so it's going to be 45 degrees times pi divided by 180 because we need to think in radians. So let's go ahead. That's the radian conversion measure, right? And so we have that. We've got our V naught, which we decided was 1, and we're all in unit, so we don't have to worry about that. T, what is T, right? So we're going to have to go figure that out. We'll manage that in a second. G, gravity is not going to change. Okay. And we use a positive value here. The negative has already been accounted for here. Be careful there. We have to like decide how to manage that, right? So, okay, so we have all that. Now let's go back over to here. And what we had done is, remember we solved for t as a function of x, and that turns out to be this terrible thing. So let's go type this terrible thing in. You know. Okay. T final, T land, the landing point of T is going to be, okay, we're going to use that last one, V naught times the cosine of theta times, okay, now this terrible fraction, okay, so I'm going to use, I guess, I don't know, yeah, tangent of theta plus the square root of tangent of theta squared plus, and then 2 times g times y naught. Oh, I didn't type y naught up there. I'm missing that. Okay. Divided by, and then v naught squared times cosine of theta squared. This should close that bottom fraction. This should close the entire square root. This should close the entire numerator divided by g. And that should close that entire multiplication. Okay? It's terrible, but it's not that bad, right? I mean, once we have it, okay, so call it what you will, but, you know, it's there. We've programmed that sucker in. Okay, I was missing something. I was missing that initial height, which is 1. Okay, do we want to label stuff? This is my angle of fire, right? It's my initial velocity. And you can put anything you want in these comments, right? So if you want to make a note to yourself, like how to run something, or you figured stuff out about your model at some point, right? Okay. And this terrible sucker is a landing point. Okay. I don't know. This should work, I think. Okay. So my time vector now is going to go from 0 by, I don't know, let's say 0.01. Let's make it every 100th, okay? Up to the time that we land. You see what I did here? So I've made me a vector that says, okay, stop when I land, and you see this t, when we highlight it, you can see it's showing up in my equation here. So that's going to be that t, which is just going to be a vector of time values. And that'll give me my x's and y's. Now, if we've done this right, we vectorized ourselves pretty good, and we should be able to plot x versus y in a blue line, let's say, okay? Let's go see what we got. And there you go. We've launched it from foot high. It went up a little bit, but not much. And then it just comes down. And I guess this is where it lands. This didn't get all the way to 0 very good. Can we go to T-land plus 1? Oops. Or is that too weird? Oh, we went way the hell too far. No, that was a bad idea. All right. Because we're missing just like 1/10 of a second, I think. Okay, but not bad. Okay, so this shows, and then we could do something like, where's the landing point? Where's the vertex? Stuff like that, right? So let's well, this is a pretty good basic model. Let's add in a landing point, right? So the x landing point is going to be, if we go over here, see. X landing point is this thing, right? So let's go make these real quick. Here, watch. Follow my thought here. This got too complicated for me, right? So, because I have to type another of those bad equations. I don't want to do that. Here, check this out. So A is going to be -1/2 times G. No, wait. We're gonna use the x versus y one. Hold on. We're gonna use this one. So we're gonna get negative G. Let's do it like this. -G divided by, and then it's gonna be 2 times V0 squared. Okay. Times, and then cosine of theta squared, right? And that's like the A on the AX squared plus BX plus C, right? So, and then the B is just the tangent theta, right? Okay, and C is y naught, right? You ready for this? So now x land, the landing point, equals what? Well, it equals negative b minus the square root of b squared minus 4 times a times c divided by 2 times a. Call me lazy. I'll have that one done. Okay, now I can do the x vertex, right? That would be negative b divided by 2 of the a. Okay. And then what else you want? Oh, the y vertex, which you can get from the it's going to be, you get it from completing the square, right? C minus b squared over, and then it's 4a, right? Or you could plug it back in, right? Either way. Okay, so now I got extra stuff we could put in our plot. How randomly cool is this? So now I could have like the x landing point, again, 0. That should be the y landing point, right? Where you hit the ground. And we're going to use a green star on that, okay? And then I'm going to use one more, and that's going to be the x vertex against the y vertex, and we're going to do that in a red star, all right? You ready? Kapow! And now we have our landing point, and we have a vertex highlighted, and all these extra things. And then you're like, oh, I really want a cooler marker. Oh, man. Can I do it in here? Help. Marker size. Really? All right. I don't know. We'll figure that out as we go, okay? Those are going to be some plot things that we would modify. Okay, so right now this is a ballistic. This is our first plot, and we can test this if we want to ramp up our initial velocity. Let's launch it more like a cannon or something like that. So you're looking at about, let's call it 100, right? Cannon goes like 100 to like 300 to 400 feet per second. So, and you'll see that you get a heck of a launch out of this thing. And then if you get too high, you have to worry about your change of gravity, right? But this isn't bad. It gives us a pretty good idea of how you can launch something, and you'll see now you're getting a nice clean one. But when we're launching just a small distance, you're not going to get quite as much just because our time value is off slightly. You know, it didn't get us exactly there. We have to add just a little bit. This is going to be our start to this, and try to make sense of what we're doing. Go ahead and try to compare against so this is kind of like a Nerf dart. So we're going to try to compare against a Nerf dart and look at our error. And our Nerf dart is going to be our sponge ballistic.